everybody. Welcome to your first online lecture on the material in matter interactions. So first I'd like to emphasize that just because you're listening to the online lecture, that doesn't mean that I don't want you or expect you to read the textbook. The lectures, as always, are meant to supplement what's in the textbook and help out with your thinking, provide examples, augment your learning, but they're really not meant to substitute for a good read of the textbook. So please don't forget that as we go forward. Okay, so without any further ado, let's launch right into Chapter 1 on interactions in motion, and we're going to talk about detecting interactions and Newton's first law of motion in this lecture. That is sections 1.2 and 1.3 in your textbook. Okay, so let's talk about interactions. The title of this book is called Matter and Interactions, and they do deal with things a little differently and have a slightly different language than you might have noticed from previous textbooks. They really harp on this idea in Chabay and Sherwood's Matter and Interactions of interactions. So let's talk about interactions for just a minute. We're going to define the interaction as a particular way in which matter, fields, and atomic and subatomic particles affect one another, for example, through the four fundamental forces of nature, which we'll talk about here in a minute. So basically, an interaction is when one object can cause a change in another object. It doesn't necessarily mean that it does cause a change, but that it can cause a change if it's interacting with that other object. So we can detect interactions. We can detect interactions by noticing changes in systems. Now, interactions or changes in interactions could mean changes in temperature, color, or, as we talk about in Chapter 1 here, changes in the motion of an object. Okay, so Chapter 1 just deals with motion, but just bear in mind that there's other types of interactions that can cause different kinds of changes. Now, in the first few chapters of your book, we're going to be pretty much exclusively using what we call the particle model, okay? And the particle model just says, or the point particle model as it's called sometimes, is considering an object like it was a single point without any size or shape. It also means that you're treating the object as if all of its mass were concentrated into that single point, okay? So you're modeling an extended object as a point particle. Now, it works well for some situations. It's going to work well for the first few chapters, but it's not going to work well for other situations. For example, it's fine to think about a point particle moving through space in a translational way, left, right, up, down, east, west, where the entire body moves. But if you're talking about the rotation of an object, well, you can't really think about a point particle rotating, can you? So it works well for some situations, but not others. So as you model objects, you should always think about whether or not you can use the particle model, or if that's not a good model to use in this case, and you do have to treat it as an extended object. Another thing that we're going to talk more about in later lectures in this chapter is the idea of vectors and scalars. So vector quantities need both a magnitude, which is a size or a numerical value, and a direction to completely describe them, whereas scalar quantities are completely described by just a magnitude. For example, the speed limit sign here just tells you, without any units, by the way, so this is kind of a stinky physics thing. Don't emulate speed limit signs. But scalar quantity here is given, so it doesn't really care according to this sign whether you're going east or west. It just wants the magnitude. So speed is a scalar quantity. It has the same units as velocity. We define a speed as the total distance divided by the total time. I'll show you the definition here. V average is equal to d over t, where d is your distance and t is your time. So that's a scalar, but it's got no direction. So for example, if you were talking to the police officer, you might say, I was going 55 miles per hour, officer. I wasn't speeding, right? But if you need to give more information, velocity will do that for you. It has both the speed and the direction. And so if you were observing something like a crime or something, you might have said to the officer, I observed the suspect traveling north on I-85 at 70 miles per hour. Well, that's a velocity. You gave a direction, north, and the speed, how fast they were going. Okay? Now, I bring this up now because one way of detecting interactions is via a change in an object's motion. Okay, that's the only type we're talking about in chapter 1. We'll talk about other ways later. So if an object's speed and or the direction of that object changes, then that's caused by an interaction with another object. Okay, so if the speed and or direction changes, then you know that an interaction has occurred. Now you might be thinking, why isn't she just saying the F word, right? Okay, so I'm saying it, force. Here we go. All right, forces are pushes or pulls, right? Forces are what cause changes in the velocity of an object. That's Newton's definition from the second law, which you might remember from your other 1000 level introductory physics class. But Chabay and Sherwood go a little further, and they say that a force is the way in which the amount of an interaction is quantified. And see, that gets to the strength of the interaction as well. If you have a stronger force, then you have a stronger interaction between the two objects, for example. Now, we can have in intro physics courses contact forces, which means there's physical contact between the two objects. But please be aware that the 4 fundamental forces of nature act through empty space where no physical contact is required, okay? And they can be quite long range. So of those 4 fundamental forces of nature, these also are the types of interactions that are going to be occurring. You've got gravity, the gravitational force between objects. Objects with mass exert forces or interact with one another. Electromagnetic forces between electric charges, as is shown in the picture. So objects with charges can cause interactions and forces on one another. There's a nuclear force between subatomic particles, okay? The strong force, for example, holds neutrons and protons together, and then the excess strong force or the nuclear force holds nuclei together. And then weak forces, they, for example, can cause a change in the type of quark of an object. If you get more into modern physics, you'll learn about those kinds of forces. So those 4 fundamental forces of nature are all field forces, and they cause all the other sorts of forces, the contact forces that you can think of. For example, if you take your hand right now and you push it down on your computer or maybe a table that you're sitting on, your hand doesn't penetrate through the table and just go straight to the floor because of electrical repulsion in the electrons in your hand and the electrons in the table. Okay, so that is ultimately an electrical force. All right, now in this section, we're going to introduce some of Newton's laws, but I think it's worthwhile to note that Newton didn't come out of a vacuum, so to speak. So the 2 thinkers that greatly influenced Newton in his development of the laws include Aristotle and Galileo. Now, Aristotle posited that a force was always required to keep an object moving. Now, from our everyday sense, this makes a lot of sense. Like if I push on something, it doesn't just keep moving forever because I pushed it once. It's going to eventually slow down and stop. And that's because there's friction acting and dissipative forces acting in our world at all times. And so he was just observing things that he noticed on his day-to-day in his day-to-day life, right? But it took Galileo to envision a world without friction. He did a lot of experiments with ramps, for example, and changing the material in the ramp and that sort of thing. And he envisioned a world without friction, where objects would move at constant velocities without an external force, okay? So Newton took these thinkers and went a step further. He formulated the 3 basic laws of mechanics known as Newton's laws. We're going to deal with Newton's first law in this chapter, but we'll get to his other laws in later chapters. He also discovered the law of universal gravitation, and he invented a form of calculus, and he did a lot of work in optics as well. So Newton's first law in his own words is, every body persists in its state of resting or of moving uniformly in a direction, except to the extent that it is compelled to change that state by forces pressed upon it. Very poetic, right? Now, you might have heard it is an object in motion will stay in motion, and an object at rest will remain at rest unless acted upon by a net external force, okay? Now, this is also called the law of inertia. And we define inertia as an object's resistance to change. The more massive an object is, the more resistance that it supplies. That comes into the second law. So, spoiler alert, I guess. Now, there's some important points to Newton's first law. So, first of all, just because a lack of change in an object's motion, that doesn't necessarily mean there's no interactions or forces at all. Remember that forces are vectors, and so if the net external force sums to 0, then there could still be forces acting on that object. If there's forces, then that means that the object is interacting with another object, okay? So just because there's no change in an object's motion doesn't necessarily mean there's no interactions or forces. It just means the net vector sum of those forces is 0. So there could be forces that are equal in magnitude and opposite in direction that sum to 0, and then that would still cause no net change in the object's motion. Also remember that uniform motion, which is constant velocity motion, which is of course same speed, same direction, no change in those two things, then that means that there's no net force. So an object can be moving, right? It can still be moving, but have no net force on it, okay? Which means that it's in uniform motion. Now, this is contrary to what Aristotle thought earlier. Remember, we talked about those dissipative forces, right? Friction and such that will cause an object to stop. Aristotle would have said, well, the impetus just ran out on that thing. But now we understand that if an object's motion changes, in other words, it slows down and comes to a stop, right? Then that means that there is something acting on that object, and that something would, of course, be the net force of friction. Okay, well, I hope that served as a nice introduction for you. If you have any questions, please do let me know, and I'll see you around.